Hey, what's up, guys? This is Chung here again. So this time, again, today's daily challenge problem number 307, range sum query mutable. So this one is a very classic range query problem, right? As you guys can see from the title. So, I want to use this problem as an opportunity to revisit the segment tree. All right. Okay, so you're given like an integer array nums, and you need to handle multiple queries for the following types, right? Basically, we should be able to update a value, and we should also calculate the sum, right? The range sum between left and right, inclusive, right? So this is exactly the two operations that the segment tree is trying to improve, right? So and yeah, and then we just need to implement this class, okay? And so here example, right? We have a range, we have a array here. That's the initial numbers, right? And then we have range sum from 0 to, and then we update index 1 into 2, and then we do a range sum again. That's how we get this output here. And some constraints, right? So we have, I think this is 10 to the power of 5, maybe close to that, 3 times 10 to the power of 4. So it's on the same scale, right? Obviously, a naive implementation will be we simply just maintain a list of the numbers, right? And then every time when we do the update, right, we simply just do an update by using the index of that of the list. And then when we do the sum, right, we simply loop through. We use the index to calculate to basically to scan this array list from left to right. And obviously, the update is all of one time, right? But this sum range is going to be all of n time. So with the same number of costs, right, can be made to update and range sum. Update, of course, this one is O1, right? But the worst case scenario is that every cost is like a range sum, which means that the worst case scenario, this is going to be O of n squared time complexity, right? So that's why it's a little bit too high, given this kind of a range. This constraints here, right? That's why we want to we want to improve this time complexity from this one to n log n. That's when the segment tree comes to rescue, because with the segment tree, both the update and the range query can be log n instead of O1 and ON, right? This is because the tree structure, right? Because in the tree structure, the log n comes from the height of the tree, right? So if the tree is kind of balanced, right? Both the update and the query will only depend on how the height of the tree, which is the log n. Yep. So and let's talk about the segment tree, right? And for this one, I'm going to use the Fenwick tree, aka the binary index tree, which is also another kind of the segment tree, because the binary index tree use the binary calculation, right, which is even faster than the regular segment tree. Okay, so let me print out the blackboard. So a simple segment tree is like this, or a binary index tree. So the root is 0, and then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So I'm going to explain why the binary index tree looks in this way. Looks like this way because the value we're looking at should be its binary value instead of the original value, which this one is like 0001, right? So this one is 0010. Okay, this one is 0011. Same thing for this one, 0100, right? This one is 0101, 0110, and this is 0111. Same thing for this one, right? 1000, okay, 1001 and 1010, right? So that's the binary value for each number here from 0 to 10. There could be more, right? But I'm just using this small one as an example. So why we define like a binary, the tree structure in this way? This is because, you know, if you look at the parent, each parent and child pair. So for example, 3 and 2. So the only difference between the parent and child is that, you know, there's only if you remove the rightmost one, then the child becomes parent, right? So for example, if 3, how can you use 3 to find 2, right? Because if you remove the rightmost one, then 3 becomes 2, right? Same thing for this 5. For this one, if we remove this rightmost one, then 5 becomes 4. Same thing for the 6 here, right? If we remove the rightmost one, this 6 also becomes 4, right? Same thing as 7. The reason 7 is under 6 is because if we remove the rightmost one, then 7 becomes 6. Okay, and this characteristic allows us to use a certain expression to quickly find the parent from the current node. And in the segment tree, so the value stored in each node is a range sum. So which means that, you know, in this let's, for example, this 2, right? So in the 2, the value stores in this 2 is what? It's 0. It's a sum value from 0 to 2. Same thing for 3, right? So 3 stores a value from the parent to the current node, which is 2 to 3. So keep in mind that, you know, the parent is exclusive and the current node is inclusive, right? Same thing for 5, right? 4 is like same thing for 0 to 4, right? And then this node also from parent, which is 4 to 5. Okay, and the 6 is from 4 to 6, right? 7 from 6 to 7, right? So on and so forth. I'm not going to write everything. And so if we define like a tree structure this way, right? And at least, you know, when we do the query, let's say we want to query the value from 0 to 7, right? So how can we query the value from 0 to 7, right? As you guys can see, there's a path, right? So all we need to query is that we just simply need to query the path starting from 7, and then we will go all the way back to 0, to the root, right? And then when we reach the root, you know, if we summarize everything along the way, then we'll get the range sum of 0 to 7, because when we go from 7 to 6, we have the range sum from 6 to 7, and then from 6 to 4, we have the range sum between 4 and 6, and then from 4 to 0, we have 0 to 4, and if we summarize everything together, we have 0 to 7. That's why, you know, the range query is log n, right? Because we only traverse from the current node to the root, which is log n time complexity, right? So that's the range sum, and we already solved it. How about the update, right? So the update is a little bit complicated because, you know, let's say we want to update the values in index 5, right? Index 5, obviously, you know, we need to update this node, this index 5's node, because that's the value it's in, right? But not only we need to update this one. There's more nodes we also want to update. Which one? Because 5 is also included in the range of 4 to 6, right? So this 6 node also needs to be updated. Anything else? Yes, this one 8, right? Because 5 is also included from 0 to 8, right? Until we have reached the end of the segment tree. Basically, when we do the update, there also be some nodes we want to update. So now we have 2 requirements, right? So first one is it's a range query. Basically, given the current index, how can we traverse back to its parent node, right, all the way to the end? And second one is the update. Basically, for the update, let's say from here we need to find all the nodes that we need to update. In this case, it's 6 and 8, right? All right, so let's work on the simple one, which is the range query, which means we only need to find the parent, right? So if we look at the binary values let's say for example for 7, right? Every time, right, we just need to remove the rightmost one, since we already talked about that, right? So let's say we have 0, 1, 1, 0, right? If we want to remove this rightmost one, so what should we do? If we can get this one, right? If we can get this one, we can simply do a subtraction, right, between these two, or subtraction is the same as XOR, right? Basically, if we do XOR between these two, we'll get what we want, which is 1, 0, 0, 0, right? Same thing for this one, right? For 7, if we can get this one, then we can simply do a XOR. But how can we get this? How can we get this version? Basically, this version is we only have the rightmost value. We only keep the rightmost one, and all the remainings will be 0. And so the way we're getting it is by doing like this. The value, bitwise end to its negative value. So that's how we get that value, And I'll show you how, right? So first, we need to understand how are this negative value being calculated in computer, right? So in computer, the way we're calculating the negative value, this is we need to convert it into what? Into its the true code complementary code. So which means that so the reason being is that in computer world, when we do the calculation, there's only a plus or add. There's no subtract, because computer doesn't know how to do the subtraction. All he knows is to do the add. So for example, if we have 1 plus 2, of course this one is equal to 3, right? But if we have 1 minus 2, computer doesn't know this minus sign. So which means the computer will convert this one into a 1 plus negative 2. Okay, that's how the computer does the calculation. So which means that we need to somehow find a way to represent this negative 2 instead of, right? That's why we're gonna use the complementary code for the original code when we need to do some calculation with the negative value, because the complementary code can represent both the positive and the negative value. Okay. And how can we get the complementary code, right? So in order to get a complementary code, we need to get we need to get its one's complement code first, and then we do a +1. So one more thing. So for all the positive values, the complemental code is the same as it itself. So we don't need to worry about that. So here we're only talking about a negative value. And so to get the complemental code for negative values, so what do we do? Let's say for example we have this kind of 0 1 1 0. Sorry, 0 1 1 1. That's 7. If we want to get the -7, how do we calculate that, right? So we have let's just use 8-bit to represent this -7, because actually in reality actually one integer has like how many bytes? I think 8 bytes, right? 8 bytes means 8 times 8, which is 64 bits. If we just write all 64 bits here, it will be too long. That's why so here I'm only using 2 bytes to represent an integer. Okay, so for 7, for -7, the first one is the first bit is the sign, right? Which means when it's 1, it means negative. Then we have -7 here. Okay, so to get the complemental code of -7, so first step is we have to do one's complement, which means that one's complement that except for the first sign bit, we reverse all the remaining bit values. So that's why the 1 stays the same, and then we have 1 1 1 1, and then 0 0 0, right? So this is the one's complement of -7, right? And then from one's complement to the complemental code, we do a +1, right? So now we have, okay, so let's do +1 here. We have 1 1 1 1 1 0 0 1, right? So this is the complemental code of the -7, which is the actual code the computer uses to do the calculation, right? So now we have this one, and so this is the -I, right? And then we do x end with what? With the original I, which is this one. Okay, 0 0 0 0, and then 0 1 1 1, right? So we do end with this one. So what's the value of this one, right? As you guys can see, so that's exactly the values we're looking for. Okay, and this one 1 0 1 0. Oh, sorry, my mistake. 0 1 0 1. That's exactly the value we're looking for here, right? Because only the last one is 1. With this one, and if we do a I minus this one, right? Or you can do a XOR here, right? That's how we get the parent value, which is 6 in this case, right? Cool. So what let's do it for 6, all right, just to make sure it is not a coincidence, right, that we get the correct value. So for 6 we have 6 is this, right? 6, so the -6, right? So the -6 is what? So 1 0 0 0, and then 0 1 1 0, right? So that's the negative value. So we get the one's complement, which is 1 stays the same, and then we reverse the remaining. So 1 0 1 1 0 0 1, right? And then we do a +1 to get the complemental code, right? So 1 1 1 1 1 1 0 1, right? So that's the complemental code. That's the -6 in the computer. And now we do a AND with the 6 itself, 0 0 0 0, right? and then 0, 1, 1, 0, right? So what do we have here? It will end here. 0. There's a mistake here. So this one, yeah. After doing the +1, we have this one, 0, 1, 0, right? So that's a -6. So, and then if we do AND with the original one, we have this 0, 1, 0, right? See, this is exactly the ones we're looking for, right? Because and then after we doing this subtraction or bitwise XOR, right, with this one, we'll get 4, right? Okay, cool. So that's how we get the parent, right? And then we simply just use this same formula, right, on each node to keep going until we reach the root, right? Solved, right? And so that's that. How about the range? How about so we already solved the range query. How about the update? Right. So for the update, like I said, let's say for example we want to update 5, right? So what we need to find? We need to find 6 and 8. But how can we navigate from 5 to 6 and from 6 to 8? Right? If you watch closely and remember this part, we get is the is this one, which is the we keep the rightmost one, right? And then we set everything else to be 0, and then we do a subtract, right? If instead of doing a subtract, if we do a add, then we'll get what we need, right? Because take a look. So from 5, so what's going to be this that's I x and minus I? It will be 0, 0, 0, 1, right? Because that's how we get this rightmost one. If we do a if we do an add plus between these two, we'll have what? We'll have this one, right? 0, 1, 1, 0. And from here, if we do the same thing, right? We have what? We have 0, 0, 1, 0, right? This is a part of this one. And if we do a plus again, what we have? We have 8. That's how we get 8. Right? See? It's magic, right? Cool. And that's how we use this same part, and we simply flip this sign here, so we can find both the parent and the next node that we need to update. And that's about it for the binary index tree. And with those in mind, the implementation is pretty straightforward. Okay. So now let's start coding then, finally. So we first we need to create the tree, right? So for the tree, it's going to be the, let's get the length first. Then it's going to be the length of numbers, right? And we're also going to store the numbers since we need to do the update later on, okay? Numbers. So for the tree at the beginning, everything is 0, and the length will be the n plus 1. So the reason being is because self n plus 1. Because the root node, remember, the root node 0 is a dummy root node. Basically, in the binary index tree, the root 0 doesn't mean anything. It's a root for everything. So which means, we will need to do a plus 1 to reserve that index 0 as the root. So which means the remaining nodes starting from 1. Okay. And then first thing first, we need to initialize the binary index tree because we have numbers. So which means we will need to we need to update, construct the tree, right? So we have for I dot number, right? Enumerate numbers. So which means we're gonna insert each the numbers into the tree one by one. And here we have update. Let me create like another helper functions here. Let's call it update tree. Okay. So here we have a self, and then we have index, and then we have a value. Okay. So here we do a self dot update tree, right? So the index is I+1 dot numbers dot num. This is the number. So here, remember, index 0 in binary index tree is reserved for the dummy root, which means we cannot update that root node, right? That's why the first actual number have in the binary index tree will have the index 1 instead of 0. That's why when we do the update tree here, we always do I+1. Okay. And now let's do the update, right? Remember, so the update is what? Update is simply just loop, find the next node that includes this index, right? That's why we have this while I is smaller than the self.n, because n is the maximum index in the tree, right? So we have self.tree.I, we increment by the value, and to find the next one, remember, that's how we find the next node we want to update, right? I and minus I, right? So that's all this update tree needs to do. Now for the range sum, right? We'll implement this update later on because after initializing the update tree, this entire tree, we can do the range sum, right? So the range sum we have left and right, and then let's define like another tree function. Let's called get sum, right? So we have self and I. So this get sum means that given like index I, it means that it'll get all the value, right, between index 0 and I, right? So answer equal to 0. And for this one, all we need to do is that from this current index, we need to find all the parents, right? And until we reach the root. So, well, I is greater than 0, because if I equals to 0, that's when we need to stop, right? And then the answer gonna be self.tree.I, right? Because each node stores the range from the parent to the current node. And then to find the parent, remember, we simply use the subtract I and this one, right? Or we can use OR, right? Bitwise OR and bitwise XOR here, right? That's how we. Regardless, okay. So and then we return the answer in the end. Cool. That's how we get the sum, the range sum. And now we have implement this binary index tree function. We can start implementing our class function here. So first is the range array, right? Remember, so range we want to get from the left and right, but here we only have one parameters, right? From 0 to I. Pretty easy, right? So we simply just do a range query twice. So the first one is the right, right? So the right, we're gonna do a right +1. Remember again, right? So every index that pass into this class is 0 based, and the index in our binary index tree is 1 based. That's why we will do a right +1 here to get everything from 0 to right, right? And how can we get the range from left to right? So we simply subtract the value from left, right? Actually, this one should be left +1 and then -1, right? Because from left to right, this is inclusive, so we need to do this one to right minus this one to left -1, right? But since we're doing this kind of +1 -1, this one will be the same as left in the end, and that's how we do the range summary, right? And pretty straightforward. And now the update. So the update, actually we're updating a value, right? We're updating values from one value to another. Okay. So how can we do this one? This one actually we can do it in a very similar way as how we initialize the binary index tree. Is we simply need to get the difference between the new value and the old value. That's why we still need to use this array to maintain that, right? So we get difference and then we do an update, right? Or we update the values in the index to the current value, and then we update the tree. It's going to be index +1 as always, and then the difference, right? So we just need to update the difference because we have a tree here, right? I mean, so when we do the update, right? Let's say we update this, this one. This is 5, I remember, right? So here it stores the range sum because if we know the difference, we simply just use that difference to update all the nodes that include 5. That will give us the updated range sum for each node. And I believe that's it. Yeah. I think this should work. Yeah, let me run the code here. Okay, accepted and submit. Right, cool, it works, right? And yeah, I think that's pretty much it is, right? I mean, the main purpose of this problem is just to implement the segment tree. In our case, it's a binary index tree, right? And this is the two parts, the two most important expression that you guys need to remember, right? How to first is this first one is this one, how to get the parent from the current node. Second one is how can we get the next nodes, right? That include the current I, which means that the node needs to be updated. And other than that is a few of minor stuff like the one base, zero base, and then this update thing, right? So it shouldn't be too hard after you have implemented this tree structure. Cool. I think that's pretty much it is. And thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.